Hi, my name is Charles McFarlane, Chief Business Officer for CodePlay Software. We have created an excellent webcast for this Kasako AI Hardware Summit webinar series broadcast just before the summit on the 13th of September. This webcast will last almost an hour and contains some introductions from CodePlay's work and achievement and discussions with technology leaders influencing the market today. All these full, unedited interviews will be available after the AI Hardware Summit. Follow our Twitter and LinkedIn feeds for more details on this. After my introduction, I will highlight some recent great news for CodePlay. But first, the interview with Penporn Koanantakul. She's a software engineer with Google leading their work with TensorFlow for kernel optimizations and integration with many hardware suppliers. The next section of the webcast will focus on RISC-V and how CodePlay is bringing OpenCL, SYCL, and the AI and HPC ecosystem to RISC-V vector implementations. RVV is gaining momentum, and CodePlay's work with NSI Texi and KMC for NEDO in Japan will provide a rapid evaluation and configuration to rapidly support the definition and development of an RVV SoC based on real software. Our second fireside chat is with James Rinders, who works for Intel and has decades of experience in parallel programming in heterogeneous systems. James is currently focused on one API led by Intel, an open source program that supports SYCL and a substantial ecosystem across multiple hardware solutions. To wrap things up, we'll have a short spotlight chat with Kevin Harms, who is a performance engineering team lead at Argonne National Labs. Kevin will discuss the use of their supercomputers as they head towards exascale performance for scientists to study all areas of science, for example, biology, chemistry, high energy physics, molecular dynamics, fluid dynamics, things that are tough to experiment and require simulation. So let's get started about CodePlay and what we enable in the world of software for AI and HPC. CodePlay is based in Edinburgh in Scotland with around 80 staff, a team of expert engineers working on open standards projects. Our goal is to make AI and HPC open and safe and accessible to everyone by contributing to open standards and delivering software platforms for many of the latest accelerators and processors. Our customers are many of the global greats, from processor IP semiconductor companies and the absolute latest supercomputer systems hosted by the US National Labs. Almost all market segments can benefit from our software, as mentioned, from the highest performance supercomputers to smartphones and advanced driver assistance systems in automotive, known as ADAS. Our product of Akaran brings all industry needs together, ensuring benchmarks, frameworks, and libraries and supported processors are validated and available. Within Akaran, we can provide Compute CPP, our closed source implementation of the SYCL open standard, Compute Aorta for many of the core technologies, and also the one API SYCL-based standard led by Intel. From AI and machine learning to HPC and vision processing, CodePlay's solutions and support are at the heart of these intelligent systems and critical to achieving the highest performance and time to market for application developers. Some recent headlines that involve CodePlay's highly respected contribution into HPC with the support for SYCL into the US National Lab supercomputers. Firstly, the announcement in February this year regarding Perlmutter at Lawrence Berkeley National Labs, allowing SYCL code created using one API and executed on NVIDIA's A100 GPU accelerators. This is the first real use case allowing millions of lines of real HPC software to be portable across multiple leading GPUs. The second announcement came in June this year with a similar motivation, that is SYCL code created using one API and executed on AMD GPUs accelerators in the Frontier supercomputer at Oak Ridge National Labs. This makes millions of lines of real HPC software can be based on SYCL and executed on all the US National Labs computers. To benefit the transition from SYCL, one API toolkit provides a CUDA to SYCL conversion tool, which when combined with auto-tuning algorithms can achieve amazing results both in portability and performance. Have a look at the recent presentation by Stefan Krisko from the Zuse Institute in Berlin entitled Migrating CUDA Stencil Code to SYCL about tsunami simulation in CUDA and benchmarked against SYCL on multiple platforms. In October last year, we announced a program to enable RISC-V vector-based systems to benefit from our OpenCL and SYCL solutions. Software developers working on HPC and AI for embedded systems will be able to take advantage of industry-defined open standards from the Kronos Group on RISC-V architectures, thanks to Japan's New Energy and Industrial Technology Development Organization, known as NEDO, in which NSI Texi and Kyoto Microcomputer Company, known as KMC, are participating. With RISC-V making credible gains each month, this process is highly relevant by embracing the leading programming needs for AI and HPC and applying them to the new vector extension solution defined by RISC-V. CodePlay has already released a pre-alpha evaluation kit to a few selected customers, with wider availability coming very soon. Watch this space for more news coming soon. This next interview is with Penporn Kwanantakul, who is a software engineer at Google and leads the TensorFlow integration with many hardware vendors, including x86, ARM, and many XPUs available to accelerate AI. Her work includes optimizing TensorFlow kernels and integrating TensorFlow with OneAPI, the open source solution led by Intel, and benefits from SYCL C++ open standard.
Welcome, Penporn. Thank you for joining us today. I'm really looking forward to this discussion. You lead the OneAPI integration into TensorFlow. Can you tell us a bit about your role, please?
Sure. Yeah. First of all, thank you for inviting me here. I'm honored to be here. And yeah, so my name is Penporn Kwanantakul. I'm a software engineer at Google. I work on TensorFlow's integration with hardware vendors and also TensorFlow kernels in general. And like Andrew mentioned, so I lead TensorFlow's integration with OneAPI. Yeah. So it's not just for Intel hardware, but also for ARM as well. We use OneAPI for both x86 backend and also ARM backend, and also to support Intel XPU devices in the future.
So what are you doing to get OneAPI into TensorFlow?
Yeah, so it started with just Intel CPU. So yeah, so we have a close partnership with Intel, and then the whole OneAPI effort started, and we started integrating with it was MKLDNN at first, and then MKLDNN became OneDNN, which is part of OneAPI standard, OneAPI deep neural network library, and we were doing that for Intel CPU. And then OneDNN added the ARM backend. So we also benefited from that because the integration with TensorFlow and OneDNN is already done. So we can just compile the option with ARM backend. And now we also get TensorFlow support for ARM.
Yeah.
And right now we are also working on supporting Intel XPU devices, which will also use both DPC++ and OneDNN underneath. But we are approaching it differently. So for CPU, when we add OneDNN integration code directly into TensorFlow repository, but for the XPU devices, we are making it a plugin. So it will be a separate binary and talk to TensorFlow through a stable binary interface.
Where does SYCL and OneAPI fit within TensorFlow?
Yeah, so on the TensorFlow CPU side, we are mostly focused on OneDNN. So we don't go and code in DPC++ directly. We mostly just call OneDNN API from the TensorFlow. So it works like this. So we write custom ops for TensorFlow, and these custom ops will call OneDNN primitives for example, convolution primitives and whatever. And these users cannot call these custom ops directly. So these custom ops get introduced into TensorFlow graph by a graph rewrite pass. So when we run the graph rewrite pass, it will go through vanilla TensorFlow ops and see what's available, and then swap that out and then replace it with OneDNN op. And those OneDNN op will be run. So the user won't have to code in DPC++ or even code in using OneDNN primitive directly. So they just need to call normal TensorFlow op, and then we will call those custom OneDNN op underneath for them.
Right.
Okay. Is just to turn on one environment variable flag, and then we will turn on that graph rewrite and we write all the applicable ops to OneDNN ops.
If you're using a cross-platform API like OneAPI, presumably you're going to worry about performance. So how do you make sure you achieve performance with one API in TensorFlow?
So we just focus on computationally expensive ops. So ops like contraction-like ops, for example, matmul, batch matmul, convolution 2D, convolution 3D, and all kind of fused version of those, fused matmul, fused convolution. And then we extend it to quantized version of those as well. And yeah, and then all the other operations that are fusible, ReLU, fused batch norm, and yeah, all the stuff.
You talked there about fusible operations. What do you mean by fusion?
Oh, we mean they can be done together in one step. For example, convolution or contraction ops with element followed by element-wise operations. Those actually can be done together in one kernel. You don't need two separate kernels, and that can save you cache memory access time, because if you just do convolution first and then do that element-wise operation later, the things that you were already doing in convolution, your tensor might fall out of cache, and you may have to reload the whole tensor again for just those element-wise operations. So by fusing them together, you can just apply those element-wise operations while you're just doing that one block is still hot in cache.
How do you do fusion? How do you fuse two operations together?
Yeah, and in fact, we don't just fuse two ops, we fuse as much as possible. And so there can be multiple operations. For example, maybe ReLU, and then you requantize stuff, and you can fuse as much as possible. And yeah, as long as it's not like two convolutions together, and that would be hard to fuse, because now it's not just block by block operation now.
Can you really generate machine learning kernels within a compiler? Can a compiler do that?
Yes, it can, and then we are actually already doing that with MLIR in TensorFlow. Yeah, we did it with a small number of kernels, but we plan to expand it more in the future.
Can those compiler-generated machine learning kernels actually beat something hand-coded by an expert programmer?
Oh, that's a good question. Yeah. So I guess, so so for the ones that we have a direct comparison with, we only deploy the compiler one when we know it's faster.
Yeah.
And we actually saw at least about 20% benefits in some case. But for the case that that the handwritten kernel is faster, there is no reason not to use handwritten kernel. So we have two paths. And we have the option to go to either of them. And also for the fuse patterns that we don't have handwritten kernel for, we can also fall back to the compiler option to use it.
Yeah, gosh, that's so interesting that you've got multiple different ways of doing the same thing, and then you measure which one's fastest, and you go, well, we'll do this one or this one depending on what's fastest.
That is the future plan. So right now it's still kind of like not that automatic. It's more like heuristic, but yeah.
Yeah. You've talked about things like MLIR and one API and things, but another library that's used a lot inside TensorFlow that we see is Eigen. Are all of these technologies going to replace Eigen?
We are still using Eigen a lot, and I don't think we will kind of like replace it in the very near future. We are still using it in many places in TensorFlow. We are also using it for thread pool. So we added a thread pool interface in the unsupported folder of Eigen, and Eigen thread pool is used as the basis of the whole TensorFlow thread pool. So a lot of TensorFlow components is relying on Eigen, and we are just trying to replace some functionality that we think MLIR can help leverage the existing issues, but not replacing Eigen yet. Yeah.
One of the ideas I hear a lot about from AI chip companies is this idea of AI stabilization. The idea is that we've invented all of the machine learning operators out there, and so therefore all we have to do is accelerate a fixed set of operations, and we could do that by hand. So we don't need some of this compiler technology. We don't need programmability.
I can't claim to be an expert here, but from my personal point of view, I think we are far from being done, both on the ML research side and also infrastructure side. So on the research side, so it's not just like, oh, we have all the operators, but it's more like how do we achieve our goals with machine learning, and right now it's not smart enough to do the generic things that we want it to do yet. And then there's also a question of ML fairness or ethical AI. How do we actually take the bias out of the model when everything we train with is actually biased? The data we take in from the internet is all biased, and how do we make a fair model and not make people suffer from the consequence of it not being fair?
Yeah.
There's also a question of interpretability. For example, if you use it in healthcare and then some ML model just say, oh, you have a higher chance of being dead in the next year or something, then people would want to know, why are you saying that, and not just like, oh, it's because the math say so. Yeah. So yeah, there's still a lot of work we need to do on the ML research side, on how to get it to do something more useful and also more fair to humans. And there's also on the side where, how do we get it to do things more efficiently? So we are scaling model larger and larger now, using more and more data, but maybe we should try to use data more efficiently, learn more from the amount of the data that we have, because we are scaling really fast and our infrastructures cannot catch up. The amount of workload and the amount of data that we are trying to feed into them requires a lot of compute, and we need a way to do it more efficiently. And we can also look at and not just by using data more efficiently, and maybe construct model in a more efficient way as well. And for example, another way is doing sparse training, so all the weights don't need to be dense, because not all of them are important. Like, for example, if you look at the human brain, the connections are actually sparse. So then, yeah, you can try to save more computation by doing sparse training. And then the question is about, how do you make it train efficiently? How do you know the topology of the connection then? How do you learn them? And that's just on the machine learning side. And then there are a bunch more on the infrastructure side, but hardware and software. Yeah.
Yeah.
Okay, so say I came to you with a chip that had incredible performance, but I'd sacrificed programmability. You would no longer be able to program that, but the benefit would be huge performance. Do you think that trade-off is worth it?
So you are relying on just existing code?
Yeah.
And on that hardware? Yeah, I don't think that would be scalable with machine learning. So at least within Google, researchers come up with new operators all the time for new models and new ways to do things. So it's very important that it's very programmable for them. Yeah.
Yeah.
Rod Burns is a VP of engineering with CodePlay and responsible for the ecosystems. With RISC-V gaining significant momentum, he is driving much of the release and support of CodePlay's solution containing OpenCL and SYCL on the RISC-V vector solution for AI and HPC acceleration. In his talk, Rod will introduce RISC-V with the benefits of open standards and then run through a demonstration application, diving into how our team accelerate the execution of a tensor-based neural network on the RISC-V Spike simulator using open source and open standard software. The same stack can be adapted to run on a wide range of processors. Over to Rod.
Hello there. My name's Rod Burns, and I'm VP of Ecosystem at CodePlay. I'm going to talk to you about how our teams are bringing together open standards and open source technologies to enable complex applications for a range of processors. Algorithms such as convolutions and pooling involve running operations on matrix and vector data structures. It's these operations that can be executed efficiently on processors that are designed to allow many common operations to run in parallel across many cores. This has become a common use case for GPUs in recent years, but companies are also looking at ways to develop more specialized processors to tackle the performance challenges of modern AI applications. During this section, we'll work through a demonstration of the running an accelerated neural network application using RISC-V on the Spike simulator, and how this same software stack can be adopted to other processor types. We'll talk about offloading work to either a GPU or other processors we might call XPUs. A GPU or XPU can process a lot more data at the same time because of the larger number of cores that are available. This makes it possible to do things like matrix multiplication much more quickly than on a CPU. However, in a heterogeneous environment, the CPU is used as a host, which means it's used to control the transfer of data and instructions to the GPU or XPU. This is what's known as offload, where the CPU offloads the execution of work to the GPU or XPU. The host CPU is optimized for latency, and the GPU or XPU is optimized for processing large amounts of data. SYCL and OpenCL are open standard APIs that enable code for heterogeneous processors. CodePlay has been involved in helping to define the SYCL and OpenCL standards for the past 6 years. SYCL in particular offers a non-proprietary alternative to CUDA, and there are existing communities working on projects, libraries, and frameworks with SYCL and OpenCL. The NASA laboratories in the US, CERN in Europe, and many other organizations are using SYCL to deploy applications to the most powerful supercomputers in the world. Go to sycl.tech/projects to find out about some of these. What CodePlay is seeing from large organizations writing complex HPC and AI software is that they're looking for software tools that bring programmability. What that means is that they have the flexibility to extend the AI operations that are supported by frameworks on specific processors and fuse multiple operations together to reduce memory access. This kind of flexibility is only possible using a programming model that gives developers this ability. The research team at CodePlay has built a neural network application written in standard ISO C++ that uses SYCL-DNN, Eigen, and SYCL BLAS, all open source libraries that are written using SYCL and implement the algorithms required for this layers of this network. The application uses the VGG16 convolutional network to demonstrate running an end-to-end inference model through the RISC-V Spike simulator. By using the SYCL-DNN library, it's possible to call various neural network operations like convolution, softmax, and maxpool. SYCL-DNN provides accelerated kernels for each of these operations, and in turn uses tensor operations from Eigen, an open source linear algebra library also used by the TensorFlow framework. These operations can offload work to the cores of a RISC-V processor supporting the RISC-V extension. I'll now run the demonstration application. Calling this command line script executes the binary for our demo program and passes it an image to be classified. The RISC-V Spike simulator is running in the background, so this is the equivalent of running on real RISC-V hardware. In this example, it finds an American Staffordshire Terrier. The demo is currently being extended to include ResNet and other networks by our research team. You can see from this graphic that the VGG network passes an image through a series of operations to run the inference. The SYCL-DNN library provides optimized operations for 2D convolution, pooling, and transform for the softmax pass, and SYCL BLAS provides a gem operation required for the fully nected pass. These libraries make it straightforward for developers to call these functions with the appropriate inputs. These high-level libraries provide an optimized set of primitives used by neural network applications, and software developers rely on these to be tuned and optimized for the processors they are targeting. So we have a classifier application using the VGG network running with SYCL, but how does it work under the hood? I'll now talk about how our Argonne platform translates the C++ code written by our research team into lower-level instructions that can be understood by a processor. Let's start with a bigger picture look at the technology stack that is needed to drive this demonstration application. This graphic shows how the different parts of this demo fit together. The Argonne platform provides some of the components for this demo. The application developer writes code that calls operations from the open source SYCL-DNN library that has kernels tuned and optimized for processors. In this case, the Spike RISC-V simulator. But equally, this could be a real RISC-V cores or indeed a processor of your own design. The Eigen library supports SYCL-DNN by providing optimized kernels and kernel fusion for tensor operations. This code is all passed to Compute CPP and is compiled along separate paths. The operations used by the neural network are too complex to show here, so I'll use a vector addition to demonstrate this journey from C++ code onto the SPIKE RISC-V simulated processor. Here we have a small SYCL program. The code on this slide contains both code that will run on the host CPU and on the accelerator device. The RISC-V vector processor is the accelerator device in this walkthrough. The program is a simple vector addition. First, we create a queue to manage code sent to the device and buffers to contain the data we'll process. The CL SYCL range num of items will be used to represent how many parallel work items will execute on device code. In this example, we have one work item per index in the input vectors. All of this code runs on the host CPU. After this, we have a device queue submit call that we can pass a lambda to. The code within the lambda will run on the RISC-V vector processor. The most interesting part of this is the body of the kern lambda. This contains code for the vector addition. We pass this kern lambda to the parallel for function, and that is how the device compiler knows that it needs to handle this piece of code. The semantics of the code are that this lambda gets executed in parallel num of item times, and our device compiler exploits its knowledge of these semantics to generate efficient device assembly. First, the device compiler will compile a single instance of the code that will run in parallel. Here we have the LLVM intermediate representation for that code from our example. Within the intermediate code, you can see two loads, an fadd, or floating point add, and a store, i.e. all the parts of a vector addition. You can also see that on the line that begins with a %1, a call to a function getGlobalID. The name is mangled because that's how type information is handled within the compiler, but the unmangled name is getGlobalID. This is how we arrange for each parallel instance of this function or work item to process a different value. This is also how we can exploit the parallel semantics of SYCL to efficiently compile to RISC-V vector instructions. The parallel semantics of this function is SPMD, single program, multiple data. That is the same single program that will run multiple times on multiple pieces of data. In this example, that was achieved using the getGlobalID call, which will return a different value for each instance of the program. This means that we can compile a set of work items to a SIMD, single instruction multiple data packet. Each packet will execute a set of adjacent work items in parallel on a single vector unit. Now you can see how the LLVM intermediate representation looks after we perform that transformation. This is still the vector addition. You can still see the two loads, the fadd and the store, but now instead of operating on a single unit, it's working on a v_1 set of inputs. If we were compiling for an architecture with a fixed vector width, such as AVX, this would be a fixed vector size instead. But the RISC-V vector ISA lets us compile to a scalable width. Now that this program represents vscale work items, the runtime code will automatically know to execute this fewer times. Finally, we compile the intermediate representation to actual RISC-V vector instructions. You can still see the two vector loads of 32-bit elements, VLE32, the vector floating point addition, VFAdd, and the vector store of 32-bit elements, VSE32. The scalable vector width is handled by using the vsetVLI instruction. We set the number of elements to be processed, and it returns how many 32-bit elements a single physical vector can contain on this hardware device. We then loop around this an appropriate number of times, and we've achieved our parallel vector addition. This same approach scales up to the operators within a machine learning graph, but the amount of code involved certainly would not fit on a slide. So in closing, understand that this demonstration is being adapted for other neural networks, such as ResNet. And this is made straightforward because SYCL allows developers to use existing common software frameworks and libraries. The fundamental operations required for neural networks already exist, and SYCL's flexibility enables new operations to be added to these libraries. This demonstration was built using open standards and open source software, with current support for the RISC-V SPIKE simulator. But the beauty of this approach is that by implementing the low-level support for other processors, The whole stack can be used by application developers. If you want to try this out on your own computer and examine the instruction output for the more complex neural network code, go to this URL and download the package.
The next session is with James Rinders, who's an engineer at Intel, with parallel computing expertise spanning 4 decades, focused on enabling parallel programming in a heterogeneous world. James is currently focused on the DPC++ project, which is SYCL for LLVM, and the One API initiative, delivering APIs spanning compute devices of many types from many vendors. James is an author, co-author, and editor of 10 technical books relating to parallel processing. His latest book is about SYCL, and there's a link there for the free download if you look in apresc.com. He has had a great fortune to help many key contributions to 2 of the world's fastest computers, #1 in the top 500 list, as well as many other supercomputers and software developers tools. James consistently enjoys writing, teaching, programming, and consulting in areas related to parallel computing for HPC and AI. Over to James.
My name's James Rinders. I am an engineer at Intel, and I'm currently working on the One API initiative, specifically with the DPC++ compiler, which is an LLVM implementation for SYCL.
You use the term XPUs. Can you explain what you mean by XPUs?
XPU is a shorthand to me for star.star processing unit. It just means whatever, a GPU, an FPGA, a DSP, parts of a CPU, anything that can potentially accelerate my program. I'd like to think about it in terms of an abstraction where I'm programming a host program and I have devices available to me to accelerate. I don't want to think about it as GPU acceleration or FPGA acceleration. There's a real opportunity here to cut the right dividing line and abstract so that I'm programming to an accelerator as somewhat generic, or at least structuring my program like it's generic. This gives me the ability to tune for specific devices, but not have to rewrite my entire program every time I get a new architecture. That's incredibly important. And so that's where the term XPU comes from, is I want to program to XPUs, and then when I actually want to know that my XPU is a GPU or an FPGA, I can write some specific code, but my entire structure of my application should be around this concept of a generic accelerator. And that sounds like it might have lots of overhead and stuff, but it turns out in reality, this can work a lot better than it sounds like it would. In fact, I think it's going to be the preferred way of programming.
So it does surprise me, as somebody from Intel, you're talking about all these new kind of processors. I suppose I think of Intel as a CPU company, but is that really the future for Intel, is a wide proliferation of different kinds of processors for different kinds of tasks?
It absolutely is. And, you know, when I think of Intel, I think of Intel as a manufacturing company. A lot of people don't know Intel started as to miniaturize and make DRAMs. Intel was the first company to productize DRAMs. Microprocessors came along as a cool thing to design. I think Intel has pushed microprocessors to their limits. There's certainly more innovation left in the future, but a lot of things have changed over the decades, and now there's a lot of diversity in programming. In the devices we can program, the processing units. And as we solve things like with One API, SYCL, we look at solving the software challenge. It really frees up our hardware designers to design more devices. You know, if you went back 30 years, there wasn't enough software in the world to survive something like this if we had tried it. But as an industry, we've learned a lot, and we have a fighting chance of being able to support software stacks on a much greater diversity. So that is Intel's future. It's everyone's future. And if we deny that future, we'll just be left behind.
Yeah, so do you think it's possible? Because, the difference between a CPU and a GPU is quite large, and then you add in an FPGA that's even larger, and then you're saying that there's these other kind of XPUs that could be doing AI or machine vision or something on top. Is it really possible to write that code once and it actually works across all, or it works reasonably well across all of them?
It is, with some caveats. The way I think about it is the refactoring shouldn't be for a device. It should be for an algorithm and the style of approach. So it turns out that a lot of problems get decomposed and can be expressed as a SIMD application, or a SIMD. SIMD is very common. And SIMD is something that's become quite associated with GPUs, but VLIW processors, AVX512 on the CPU, you can implement things on an FPGA. They can be SIMD. So I like to think of it in terms of, if I have an algorithm that's been factored in terms of SIMD, how many devices can support me running that? Now, I may come up with a radically different idea if I'm using a certain AI chip. I might want a graph-oriented algorithm. And in that case, we aren't magically going to convert a SIMD algorithm to a graph algorithm. But if I have a graph algorithm, there's a lot of devices that could potentially accelerate me. Or if I have a SIMD algorithm, there's a lot of devices that, and as a programmer, I'd rather code that way and then associate with devices that can support me, rather than start with the idea of let's just program to a particular device.
Somebody designs some new innovative XPU and it's got some special feature on it, and I want to use that feature, but that feature isn't in the SYCL standard, or it isn't in one API. Does that mean I can't use it?
Oh, not at all, because the SYCL standard, the first thing the SYCL standard does for us is give us control to find devices, to locate them, so forth, to associate memory with them. All of those things can stay the same, or at least we can understand them. What we're talking about is what we call a kernel, which is just usually a pretty short piece of code. Well, I shouldn't say that. It can grow to be hundreds of thousands of lines in some cases, but it's conceptually a small piece of computation. You're doing a specific task, and that's what you would potentially rewrite. And for a lot of generally programmable devices, if it's a generally programmable XPU, compiler and tools can help a lot. But sometimes the innovation for an XPU is to make it less programmable. That's often a path to higher performance. And in those cases, the kernel doesn't actually have to be even written in C++. There's a lot of latitude there for the kernel. Can be written in something more exotic if you want. And we're seeing some instances of that. We'll see how much that takes off, but at least then I still preserve the general structure of my program. And that's worth a lot more than some people give it credit for, a lot more. And rewriting an occasional kernel because I know that I think, can get better performance by rewriting that section of code is infinitely preferable to throwing the entire thing out and rewriting an entire program hoping I'll get better performance.
And we know this is being used in huge supercomputers. Do I need a supercomputer to make use of this? How small can it scale? Because we see heterogeneous devices going down to, today's smartwatches, for example. Very small IoT devices are using heterogeneous processing to achieve a lot of efficiency. How low do you think your XPUs can scale before SYCL isn't useful anymore? Well,
I think of XPU as an abstraction. I don't worry so much about the exact devices I'm abstracting to. And when I think of it that way, it's everywhere. I mean, anyone working in embedded with phones and watches and anything else like that, they've been doing heterogeneous for a long time. The real question we're trying to attack is how accessible do we make that to programmers? So I think this abstraction, this idea that I wrote a program and it can easily find and use accelerators, that applies to all devices. I have no doubt. I see enormous opportunities for it on desktops, laptops, cell phones, watches, and all the way up to supercomputers. This is the future of computing. The future of computing is not computers based on just a CPU or just a CPU with a GPU. There's a lot of innovation available to us in the hardware. The key is making sure that that innovation is accessed by software developers, because if we don't make the problem tractable for software developers, it makes it harder for hardware developers to innovate.
That's great. And if I want to learn more about SYCL or OneAPI, how do I learn about how to use it or bring it to a new processor?
Well, that's an interesting question. If you're interested in programming it, learning about it, and so forth, of course, I have to plug the fact that I helped write a book about SYCL programming. It's called Data Parallel C++, because it's really about bringing data parallelism to C++. If you're more interested in the implementation details and so forth, I would suggest you get involved with the OneAPI, maybe participate in the technical advisory board, meet some of the people involved there, because there's a lot of interesting tribal knowledge, if you will, about what happens behind the scenes to enable this, what works and what doesn't work. But I would say anyone that's involved with OneAPI or SYCL is an eager to share what they've learned and so forth with anybody else that's going down this path.
Next, we have Kevin Harms, who is a performance engineering team lead at Argonne National Lab's Leadership Computing Facility. He works in the general area of system software, programming models, and storage. His primary focus of late is SYCL and high-performance storage and I/O. CodePlay's distinguished engineer and chair of the SYCL standard, Michael Wong, will discuss with Kevin the use of their supercomputers as they head towards exascale performance for scientists to study all areas of science, biology, chemistry, high-energy physics, molecular dynamics, fluid dynamics, many things that are tough to experiment and require simulation.
All right, hi. Hi, everybody. Today, I have the great pleasure of talking to Kevin Harms of the Argonne Leadership Computing Facility. And so I'd like to introduce Kevin first, and also ask Kevin to introduce yourself and say a little bit about what you do and the organization you work with.
Hi, thanks, Michael. Thanks for having me on. As you said, my name is Kevin Harms. I work at the Argonne Leadership Computing Facility. At the ALCF, I'm a performance engineering team lead. And so the performance engineering group focuses on programming models, system software, and optimizing application codes for the machines that we have.
Can you share your experience with open standard software for HPC a little bit?
Sure. I've been in HPC more than 10 years now. And when I started, we had codes that were MPI and OpenMP using C and Fortran. And so that's evolved over time to where we presently are, where we have significantly more C++, but we still have C and Fortran. And along with OpenMP and MPI, we now have some other programming models, one of those being SYCL. And so that's kind of our kind of current experience.
I'm glad you mentioned SYCL, and I guess by inference, OneAPI. Something to ask about, this is partly because Argonne and ALCF has decided to select SYCL as part of OneAPI as one of their programming models. So when did you guys decide to go towards SYCL and OneAPI, and what was your motivation?
Well, when we started on the road to acquiring this new machine that's going to be accelerator based with GPUs, we started looking at different programming models that were available. And there's always a strong desire to have something has potentially open source implementation, but also open standards. And that allows us to influence the standard in some way to benefit our users. And of course, at the time, OpenMP was developing some of their target offload, but that was still a less mature at the time we started this process. and we were looking for something that's been a little bit more mature, and SYCL has been around for quite some time and looked like an ideal target since it had multiple implementations and it had an open standard body that was behind it. And so those kind of fit our ideal points.
Good. As you know, I used to be the CEO of OpenMP, so I was involved with some of the work there. And it's interesting that you point out that despite that, you were still wanting to go towards SYCL because of the C++, I guess, the C++ implications and the workload increase in that area. Yeah. Yep. How would you estimate the increase in workload has been from Fortran to C to C++ over the years? Have you noticed any shift in that area?
It's definitely so obviously there's many legacy codes in HPC that have been 10, 20, 30 years. And so you get, for example, an old Fortran code, it just keeps going, right? People just keep augmenting the Fortran. Recently, with the shift of adding these new heterogeneous architectures, it sort of forced people to think about, okay, I need to make more significant changes. I can't just add something new to my legacy code. You want to do something different. And so if I'm going to do something different, I have the choice to do something a little bit larger. And so we see a number of teams choosing to use C++ as their desired vehicle. And so having something that works in the C++ realm became significantly more important. We still, of course, have interest in the older codes, but there's just a huge influx of people doing rewrites now, choosing a modern language.
Models within one API. This is probably one of the things that you'll be using.
Yes, for sure. Obviously, we don't have any, we don't require people to use one programming model or another, but the ALCF has spent a lot of time looking at different programming models, and SYCL has become one of what we believe will be a preferred programming model. And of course, we'll support others, but we'll help people convert codes to use SYCL and to help them optimize codes that do use SYCL.
Yeah, I dare say that
a wider one API.
Right. I dare say that I know that you guys put probably more effort than anyone else that I know across industry, academia, at evaluating programming models, because that is so important to you guys. So I trust you guys in terms of what you're doing. But so on the programming models, my favorite subject, I've been kind of a programming model scientist for 20, 25 years now. Why SYCL? I think this is a question that other people has asked. I think I know the answer, but I'd like to find out where you guys came from, because as the CEO of OpenMP in the early 2010s, I know that OpenMP has been the favorite programming language for 25 years and probably will be for many years to come. But now, why move to SYCL? Why move to another programming language?
Yeah, I mean, we'll still continue to support OpenMP, and I think it'll still be an important part of our workloads, but we also wanted to have an accelerator focused programming model, and to allow people to extract the highest performance. We also believe it might be a little bit more, let's say, nimble than OpenMP, and so provide people an opportunity to explore, because GPUs have been around for a while, but now we have a lot of codes moving into GPU enablement or accelerator enablement, as well as probably future accelerators. And I think having SYCL as a programming model available for our applications developers is going to be important, because I think there's going to be a lot of architectural changes over the next 10 years. We're also interested because it had an open standard. HPC is a niche and a niche type market, and this gives us an opportunity to take all of our users' desires and try to influence a standard, bring things into the standard that we believe will be good additions, not just to HPC, but to the wider programming populace as machines evolve, because we tend to be on the leading edge. And so we think stuff that we would like to do is going to eventually trickle down to the wider scale programming, and we just want to be at the forefront of that.
So my experience has been that your hardware might last 5, 10, 15 years before some replacement program comes in. And then software needs to last, your workload needs to last well beyond that. So is that the reason why you guys look towards open standards like SYCL or other ones like ISO C++, or any ISO standardized language to support that drive? Does it drive you crazy having hardware replaced so frequently?
Yeah, exactly. We do like to update our machines, and yeah, we like a 5 to 7 year service cycle. Mm-hmm. Usually at that point, like the power to performance ratio is shifted enough that it warrants bringing in a new machine.
That's why. Okay.
But exactly to your point, people don't want to rewrite their software every 5 to 7 years. They like it to run for 30. And so having something as an open standard that, we never know what our next machine might be, from which vendor or which type of components it might have, that will evolve over the next 5 to 7 years. And so we need something that can be adaptable and that any newcomers can come in and say, okay, well, there's an open standard, we can implement this and provide you a potential resource for your center. And so, those elements are critical to the longevity of software.
You speak to the point that you said that you never know when your next machine will be. In fact, during my 10, 15, 20 years of tenure in the high performance computing, supplying from a vendor side, I've seen you guys rotate from IBM, Intel, Cray. You seem to I don't know if it's deliberate, but it almost seems like you're deliberately rotating from machine. That's not the case, right? It just feels like one after 5 or 6 years, you go to another vendor, and then you go to another vendor.
Yeah, we have a competitive bid process.
Right.
So we don't particularly set out choosing a machine, but we of course create the requirements for it. But we may end up with a different vendor. And so we like to establish partnerships with all vendors and keep those going through the duration of our center's lifetime. So, and having something that we can work with all vendors on. So if we have an open standard, we can go from one vendor to the other, and not just yes, our users are insulated, but also we can have a working relationship, multiple vendors at the same time, working toward a common goal of making code run better on whichever platform we have.
So I do understand that A&L is not a traditional for-profit organization. In fact, I think you guys are much more closely aligned with the University of Chicago. Are you not?
Correct.
Yeah. So what were the metrics you guys might have used to measure success? I would say, talk about that in terms of developer efficiency, performance, code, reuse, refactoring, the ability to select algorithms early in the development phase for your target, things like that.
Yeah, it's hard to pinpoint a hard metric. We do have metrics for success, which there's this exascale computing program that has many projects underneath it, each with potentially multiple codes. And so getting all those running on Aurora, if we do that successfully, that'll be our metric for success. But in order to enable that, going to the things that you were asking about, it's hard to define those specifically because we don't work as closely with the team, so directly measuring their throughput. But what we do is go in and evaluate programming models and look at, okay, how hard does it look like to adapt some CPU-only code to now an accelerator-based code, and what will it take in this programming model to do that? So we do look at things like developer efficiency, like how difficult will this to be, and then definitely performance, like how much performance will you get out of doing this transformation in, let's say, the simplest possible way. Like I'm sure every programming model can get the highest possible performance from any particular piece of hardware if you put in enough work. But we want to know with, some standard basic level of effort, can you get 80% of the performance? And that type of thing is a key metric. Like how quickly can we adapt a code to run on the system and get something reasonable performance, which like 70 or 80% of what an optimized code might get.
I hope you've enjoyed this series of presentations and interviews. Please reach out to me or visit codeplay.com for more information. Also follow us on Twitter and LinkedIn for the latest headlines, and especially the unedited full versions of these videos. Thanks for your time today. Thank you.